lecture. I want to start with showing you something new which I didn't have time to show you last time, and I got some questions from you actually about it, so I want to show you this time. Here's a very simple equation: 2 to the power x is equal to 3, and I want to find x. What is the answer? Well, maybe something. Yep. So somebody said, okay, let's apply logarithm. What kind of logarithm? What base? Yeah. Okay, let's try. So let me record the first possible solution. I will apply logarithm to base 10 to both sides. Why is it better? Because I have rules how to operate with the logarithms. It takes powers to products. So it is x times logarithm to base 10 of 2. And it is logarithm 3 to base 10. Okay, wonderful. I have my answer. X is logarithm of 3 to base 10 divided by logarithm of 2 to base 10. Okay, I have one solution. That's not the only possible solution. Here's a completely different one. Well, seemingly completely different. In this problem, x by definition is logarithm of 3 to base 2. Why is that? Well, logarithm of 3 to base 2 is the power to which you should raise 2 to get 3. Just definition of logarithm. Okay, so I have one answer. I have another one. Maybe yet another one. What was so special about base 10 here? Basically nothing. It was, well, somebody's favorite number. If I were to ask in this part of the room, maybe 7 was the favorite number of somebody. So it doesn't really matter how what base I choose here. I can replace 10 by any base. I can say, well, x is logarithm of 3 to base any base b divided by logarithm of 3 of 2 to any base b. Same thing. And of course, if you listened last time and you listened that the natural logarithm is for some reason better than all the others, then you'll get a solution for some kind of particular case of this one. X is 1 of 3 divided by 1 of 2. Here I got 4 seemingly different answers. They look, well, they do look different. Is it possible to get actually different answers to this problem? Well, no, because my function is, well, this equation has only one solution. The function 2 to the power x is consistent all the time. So my function looks like this. And there is exactly one point at which it crosses y equal to 3. And we found it. However, 4 different methods gave us 4 seemingly different answers. What's the trick? I mean, it feels somewhat wrong. What would solve the problem? I mean, how is it possible that this is a solution, this is a solution, but they look different? Well, if you take your calculator, you'll find out that they are not that different. They're exactly the same number. This one, that one, this one, and for whatever choice of v you get here, they're the same number. Yeah?
I think it's because like the bases, it doesn't matter what the bases, as long as 2x and 3 are have the same base for log?
Yes, exactly. So in fact, this kind of arguments show that there is a formula for changing base of logarithm. If you want to express logarithm of any number to base b, well, you can instead compute, for example, 1 of a and divide it by 1 of b. Or you can compute logarithm to base 10 of a divided by logarithm to base 10 of b. Or for that matter, you can choose any base here, still the same answer. So there is a way to go from logarithm with one base to logarithm with completely different base using these formulas. In particular, this number and that number, they're the same number. Oh, so let me maybe, before I finish with logarithms, I'll give you a kind of small puzzle. Show using this formula that logarithm of a to the base b is the same as 1 divided by logarithm of b to base a. I mean, it's not the most important formula, but just it looks cool. Kind of. You can change a and b, and now the logarithm gets inverted. But this formula will be helpful to us. So this formula is, well, I mean, of course, I will remind you later in the course, but we will use it eventually. Okay, so now we know that actually it doesn't really matter what base you choose, as long as you are consistent in all the calculations. Okay, so maybe any questions about logarithms? Okay, so if there are no questions, we will move to kind of business problem. So it's a problem about an imaginary firm, company, operating in the imaginary economy, and the purpose of this problem will not be really to kind of solve a complicated economic problem. It will be just introduce some basic notions. So the mathematics will be very simple, but just the notions, well, might be new to some of you, or well, at least the notation may be used to somebody. So the problem is like this. Opel Incorporated produces Opels. Opel estimates that when the price of the Opel is $200, the weekly demand is 5,000 units. For every $1 increase in price, the demand drops, and it drops by 50 units. Fixed costs on a weekly basis. I will explain all the notions, so that don't worry. So fixed costs on a weekly basis are $100,000. So while you're copying, let me just tell a little bit about what the problem is saying. So we have a company, and it produces some product called open. And inside of this company, some analysts maybe they analyze the market and they conclude that if the company tries to sell the product at $200 each, then 5,000 units will be sold. And also they somehow estimated that if they try to increase the price, if they increase it by $1, the number of units sold will drop by 50. If they increase it by $5, the number of units will drop by 50 times 5. Okay, so that's about the analysts in this company. Other component is, well, the company is producing something, it has maybe a plant, it has to operate this plant. So it turns out that just for a week of operating this plant, it doesn't matter how many units you produce, just for there being a plant, you have to pay $100,000 every week. And finally, to actually produce 1 unit, well, you need some materials, you need some wages, you need to pay some wages, so you'll have to pay $75 for every unit to be produced. Now the questions. First question. Find the demand. So first of all, what is a demand equation? Basically, demand equation is just dependence between the price and quantity that you are able to sell. Or vice versa, between the quantity that you want to sell and the price at which you will have to actually sell this quantity. So in general, demand equation is dependence between price and quantity sold, quantity produced. So we'll always have some notation. Small p will stand for the price. Small q will stand for the quantity. And the demand equation is just a function. It tells you what is the price as a function of quantity. So it tells you if you want by the end of the week to sell few units which you produce, you'll have to sell them at price P. So you can take this equation, plug in the quantity, and the output is the price, which you will be able to sell this amount. And, well, kind of mathematically, usually you can express it either way. Quantity is a function of price, or price is a function of quantity. Usually people prefer to work with price as a function of quantity because well, companies usually don't operate in a monopoly, they don't operate in an economy where they are the only producers, and they're usually not able to actually set the price. What they can do is just, well, adjust their quantity to fit the price. So usually we just, well, the variable that we can change is the quantity. Well, let's see. So in this particular problem, we want to find the dependence between this price and quantity. And we are basically given some data already. We know that when the price is $200, so when the price is 200, the quantity is 5,000. This is just given to us. Now I want to express the second condition which is given to us. That for every $1 increase in the price, the amount of opets which will be sold decreases by 50. So how would I write it mathematically? So the question is, I want to write some kind of equation that expresses the following idea. For every $1 increase in price, the demand drops by 50. Yeah?
Negative 1 over 50.
Negative 1 over 50 of what?
E equals the line.
Okay, maybe it's something simple. I mean, it's not. I mean, it is almost correct, but I want something simpler. Yeah.
Q of 200 plus n equals to 5,000 minus 50n.
Okay, yes. So the idea is as follows. If we set the price at 200 plus some increase n, then the output, the quantity produced, must be 5,000 minus 50 times n. So for every $1 increase in price, the quantity produced will decreases by 50. Quantity sold decreases by 50. Okay, so it's indeed very straightforward translation of these traits. The only thing which is kind of not good about this line is the presence of strange n. I mean, n has no real, well, no meaning. It is kind of the difference between the price and 200, by how much the price is larger than 200. So let's actually eliminate it from here. Let's write, and of course we can do it. We see that there is a dependence between price and n. So if we use that n is price minus 200, we can actually derive the demand equation. So we get that the dependence on amount on price is 5,000 minus 50 times 200. Oh, sorry, e minus 200. Or if you wish, it is 15,000 minus 50 e. Yeah.
Isn't that QN?
U of n?
Yeah,
No.
because you replace P with N.
So here, my function, well, it was, as you see, expressed in terms of n.
Yeah.
But what I wanted is to express it in terms of the price itself. And then I found the dependence. N can actually be expressed in terms of the price from here. And now I have my function expressed in terms of the price. Okay, and now finally we can actually write the demand equation. I mean, there is nothing really wrong about this one, but the convention is to write demand equation as dependence of price on the quantity. So from this equation, we want to express the price as a function of quantity, and finally we get that the price is 15,000 minus Q. Price as a function of quantity is 15,000 minus Q divided by 50, or 300 minus Q over 50. Oh, so now you see the is minus Q over 50. Okay, great. So now we have this demand equation. Let's maybe try to visualize what it says. Let's plot the price as a function of quantity. So what do we see here? If the quantity is 0, the price is 300. And if the quantity is 50 times 300, which is 15,000. The price is 0. And otherwise my function is linear. Constant plus another constant times the parameter. So it just connects these 2 points. So what do we see from this graph? Well, we see that if we try to sell the OPEDs at $300 each, we'll sell just nothing. The market won't accept it. If we try to give them away for free, well, 15,000 people will have new OPEDs. And in between, as your price decreases, the demand increases. Very logical. The smaller the price, the more buyers you have. So, this model might be reasonable, might be not reasonable. Maybe you don't believe that when price is 0, this is not really infinity, but just 15,000. But anyway, that's the model. Okay, so maybe any questions about this demand equation? Yeah. Okay.
So how should that Q function so is that 50,000?
So I just solve this equation, Q is equal to this minus 50p in terms of P. So I move P to the left side and Q to the right side. So I get that 50p is 15,000 minus Q. Yeah?
I don't understand how you got n equals p minus 200.
This one, so
Yeah.
here I see that, well, in this equation I say that when my price is equal to 200 plus an increased n, then something happens. So already here I see my dependence. The price is expressed in terms of n. But now I want to eliminate n. It means I want to express n as a function of p. Well, I just solve this for the variable n.
Oh,
So you see, this is the same as this. Yeah.
how do you get 15,000?
15,000. Well, so it's 5,000 minus 50 times 200. 50 times 200 is 10,000, and it comes with a plus sign. So it's just arithmetic. Yeah. Okay, so to go from this line to this line, maybe I'll write it here. Here I have a dependence. Q is 15,000 minus 50p. Next step, I want to express p in terms of Q. So 50p is 15,000 minus Q. I just move this part to the left and this part to the right. Finally, I find it. Okay, sorry. Guys, let's continue. So we found this demand equation. Next part is, let's see what the next question is. The next is find the weekly cost function. Okay, so we'll erase everything up to here because we have already recorded in mathematical terms. So now V asks us to find the cost function. And the usual rotation is capital C as a function of Q. So first, what is it? Well, it's just the amount of money that you have to spend to produce new units. So how would we find such a thing in this particular code? Yeah. Right. So the answer is almost written here. To produce Q units, you will have to pay the following. You will have to pay $100,000 for, well, plant decoration and so on, just fixed costs. 100,000. This part doesn't really depend on Q. You just have to pay it. Because, well, you have a plant, you have to operate it. And then for each unit, you will have to pay $75 for material, for salary supporters, and so on and so on. So for each unit, you pay $75. So the total amount that you pay is 75 times the number of units. Well, that's it. Basically, no other costs are given to us, so that's the answer. So this part was really simple. Next part. Will be the first accounting term. Find the revenue. So first, let me tell what revenue is in general. The revenue is just, well, the amount of money that you get from your sales. So you sell some amount of units, and for them the buyers pay you some amount of money. This amount of money is called the revenue. So once again, it's a pretty simple concept. The question is how we define it. Okay, so the suggestion was that it was something minus cost. So what I'm saying, well, the way what revenue is just the amount of money that you get from sales, directly from sales. It's not about the cost. It's not about how much you spend. It's just, well, you sell some units and you get money from buyers. It's this amount of money. Yeah? Right. So what revenue is? All this. It's just, well, you sell Q units, and each unit sells at a price P. So for example, in this problem, it was given for us that if the price is, say, 200, then the quantity is 5,000, and then the revenue is the product, 200 times 5,000. But in general, well, we don't really know how many units you will sell. So the general equation is just the number of units times the price for each unit. So this part is very, very general. It's not problem specific, it's just common sense. The problem specific part is, well, how this price depends actually on quantity. We know that if you want to sell more units, you'll have to set price lower. If you want to sell less units, you'll set higher price. So in our problem, the revenue is, well, here I have it. My price depends on the quantity in this particular way. Q times 300 minus Q divided by 50. And let me rewrite it as 300Q minus Q squared over 50. So you see that my revenue function is quadratic function. It has something times Q plus something times Q squared. And I hope you know how quadratic functions look like. Let's try to draw this function. So we have quantity here and revenue here. So first some points here on this graph. When Q is equal to 0, you see that the revenue is 0. So this point will be on my graph. What other point can I use? Q is equal to 50. Okay, it will produce me, of course, some point, but I will have to make some computation. There is a simpler one. 10 is also close. 3,000. Might still be a little bit more complicated. So what I'm trying to get is, let's take Q over 50 equal exactly to 300. And we kind of know even what this number is. It's 15,000. So when Q is 15,000, the revenue, this factor in this product actually vanishes, is 0. So my function is 0 once again. And otherwise, it looks like a parabola, which is facing downwards because of the negative sign here of this coefficient. So it looks, well, approximately like this. And of course, we can try to understand how tall this parabola is. So at the peak here, where x is right in between these two zeros, so it's 7,500, we can actually find what the revenue is. Unfortunately, we will have to plug in this number and actually find out what this expression is equal to. Turns out to be $1,125,000. That's it. So there is some value here, about 1 million, which corresponds to quantity 7,500. So before I go on, let's try to explain what are these points. First point, 0, 0, is very simple to explain. If I sell 0 units, of course I get 0 money. Obvious. But here's something a little bit stranger. Here's, I sell a whole lot of units, 15,000 units. But still, the graph tells me that I get 0 money for it. Is it reasonable? So how? Right, because to distribute 15,000 units, I will have to distribute them for free, right here. So it is reasonable that my revenue, the amount of money that I will get, is 0 here. And in between, it is positive. I sell some units, I get some money. Okay, so very good. We have this part. We are usually, well, a company usually is not interested in maximizing its revenue. The revenue is not really a meaningful number. It's just, well, some entry in accounting book. You just record how much money you received from the buyers. What you are actually interested in is how much richer you are in the end of the week versus what you started with. So this is called the profit. Next part is find the profit. So as I said, the profit is how much money you can actually put into your pocket after a week. After all the sales, after all the spendings, how much money do you have left? And well, unfortunately, profit also starts with a P, like price. So we denote profit by capital P and price by small p. And I will use this notation. P is the bar in the bottom. I hope it won't be very confusing. Okay, so how do we find the profit? Right. So the money that I will get is the money that I get from sales minus the money that I spent for actual production, for well, the money that I spent during the week. So my profit always is the revenue minus the cost. Once again, very general equation. And I hope it makes perfect sense. It's just the amount by which you get richer is the amount of money you receive minus the amount of money you spend. And in this problem, we already know what is the revenue and what is the cost. So the profit as a function of Q is the revenue, this thing, minus the cost, which is this thing. Plus 75. So is 225Q minus Q is 750 minus 100,000. Okay, now we know what the profit is. Let's continue. Next part is about break-even points. Find the break-even points where revenue is equal to the cost. So the business might be interested in the following information. It has to spend money to operate. And, well, on the other hand, it can make some money from sales. The question is how much money, how big should the sales be so that in the end it will break even. The amount of money that it spends is the same as the amount of money it receives from the sales. Right, exactly. The profit at this point must be exactly equal to 0. So we have this equation, we must set it to 0. Profit as a function of Q is equal to 0. It means we have to solve this equation. 225Q minus Q squared 50 minus 100,000 is equal to 0. Let's rewrite it. Let's multiply by 50 and eliminate the minus signs. So minus 50 times 225 plus 50 times 100,000. The next question is just how to solve it. It's a quadratic equation, and hopefully somebody remembers the formula. So it should be right. Okay, this square is part of the formula, so we're building square root of 50 times 225 squared minus 4. Or that's not long enough. Okay, so you write it here and then write it here. Sorry about this. So the equation was Q squared minus 50 times 225 plus 50 times 100,000 is equal to 0. Record this cost function. I will need it later. So it's 100,000 plus 75. Now use this space. Okay, so quantity is we have 1 cup. Well, we have 2 in the denominator. We have this number 20 times 25 plus or minus root this number squared minus 4 times this like this 100,000. And we get some answers. We can take our calculator and find what the answers are. They are 5, 6, 2, 5, plus or minus 125 to the root of 17.5. Well, it might not be very illuminating what these numbers actually are. We can further approximate. See approximately what they are telling us. They tell us 463.5 or 10,786.5. Okay, first remark, you should remember how to solve quadratic equation. If you don't, just open the book and recall. The second remark, well, quadratic equation often has two solutions, as it does in this case. So there is not just one break-even point, there are two of them. How is this? Well, how can we see it on this graph? Questions? Sorry? It is, oh, sorry. It is two answers, I just write 10,000.
Oh.
Sorry. That's an actual comment. Sorry about this. Two answers. Of course, two answers. Actually, we can see how this works on this graph. So, on this graph, these points will correspond to points where the revenue is equal to the cost. On this graph, we already have the revenue. We still don't have the cost on it. So let's try to draw this line. When quantity is 0, the cost is pretty small, 100,000, compared to other numbers here. As the quantity increases, the cost increases linearly. And you can compute that at 15,000, it is about 1,200,000, something like this. So it looks like this. So here we go. When quantity is 0, our cost is something, it is positive. We still have to operate the plant. And the revenue is exactly 0. So we are in negative territory. We spend more than we earn. Then our revenue increases pretty fast. At some point we have this break-even point where the revenue is exactly the same as cost. So here we have this point 463. Well, then we sell more and more units, but the revenue at some point starts to decrease once again, because we are trying to sell at a price which is too high. People don't want to buy the product at this price. And the revenue decreases. But the cost keeps climbing. The more units we produce, the more money we spend for that. And at some point we get another break-even point. So that's the second answer here. 10,786. So at least it makes sense that we get two answers. Well, what's good about finding these break-even points is that now we can draw how the profit function looks like. So the next part, EL. Sketch this function. So just how does it look like? That's very simple now. If you look at this function, we see it is a quadratic polynomial. Once again, some number plus some number times q plus some number times q squared. The leading coefficient is negative, so it looks like a parabola which is facing downwards. And we already found 2 points on this parabola. This profit is equal to 0 at this point and at this point. So here we have it. At point 463.5, we have a 0. At another point, then 786.5, we have another 0. And we have a downward facing parabola. And actually, unlike the revenue, which, well, cannot be negative, the profit can be negative. We can spend more than we actually get in return. So we continue to say that here is actually negative. What is this point, by the way? At this point, we receive 0 in return, but we have some costs, fixed costs, 100,000. So it's minus 100,000. And it continues here. So it looks somewhat like this. Yes. So at this point, it's a point where quantity is 0, so we produce nothing. So we get nothing in return for our sales, but we do have some costs, the fixed costs. Well, you know, it happens. You don't get materials at some week. It does happen. Okay, finally, the heart of the problem. We want to solve the problem how to maximize the profit. So, part G, find quantity maximizes profit. So how do we go about this? Okay, so one of the answers is indeed equate the derivative to 0 and continue and so on. But well, at this point in the course, we still haven't worked with derivatives, so I don't want to involve derivatives. I want to keep the math as simple as possible. So maybe other solutions. So maybe somebody else. So, yeah.
Find the maximum point is in the difference of the two divided by half.
Okay, yes. So my function is a parabola. It is symmetric around this vertex, around this maximal point. I want to locate this point. Well, it is exactly in between these two values, just by properties of the parabola. So my quantity is the average of these two numbers. It is one of the solutions plus the other divided by 2. So let's do it. It's 5, 6, 5 plus 125 square roots, 75 plus the same thing with minus sign. And divided by 2. So this 5,625. So first conclusion, we actually, without any complicated tools, we solved this maximization problem. We found the point where the profit is maximum. Second remark, this point is not the same as the point that maximizes the revenue. The revenue is maximized at 75 hundredths. But the revenue is really not the same as the profit, because there are costs and they are not only fixed. To produce extra units, you have to pay something for every unit. So you see in this example that the point that maximizes the profit is different from the one that maximizes the revenue. It is important. And okay, so maybe any questions about this? I'll just summarize what you should take from this problem. So first thing, you should actually remember all the notations. So P, Q, cost as a function of Q, revenue as a function of Q, profit as a function of Q. So you should remember what each of these letters mean. And you should be able to use them in previous exams and so on.
Like in the test, are these going to be the same for
Yes.
non-electric profit?
So these are pretty standard notations. So this you should just remember. Another thing you should remember is that the convention is that the demand equation is price as a function of quantity. So you can explain it to yourself in one way or the other, so that you won't switch P and Q here, but you'll have to remember it. And also you should understand some pretty simple things, but it's better, well, if you both remember them and understand them. So one of them is revenue is price times quantity. Another one is profit is revenue minus cost. So very simple equations, very, I mean, they make perfect sense, but you should know them. You should understand them. Okay, so let's now leave this business context, but as kind of condition, I want to say that here we maximize a function. And if you look at this function, at the point of maximum, what happens? The tangent line at this point is exactly horizontal. It means, well, if you take a line and you put it lower and lower until it starts intersecting the graph, well, this horizontal line at this point will be tangent line. It will intersect this graph with small neighborhood just in one point. So a maximum of a function is related to a point where the tangent line is horizontal. So to maximize functions, it is, well, useful to know how to find when a tangent line is horizontal, or generally what is the slope of a tangent line to a graph. So the next part will be about slope of tangent line. And we won't do it right away in this generality, we'll just do one example. Find slope of tangent line. The graph of f of x is 2 to the power x and x is equal to 0. So I take a familiar function, 2 to the power x, the exponential function. We know how its graph looks like. And the question is, here we have a point, what is the slope of tangent line? What is the slope of this line? Oh, so maybe any ideas about how to go about this?
Well, we need to find two points, right? So that we can kind of identify the slope of the same one point being extremely close to each is
Okay, yes. So the idea is, well, a line which is really tangent to a graph is hard to find. I mean, how do you express the fact that it's tangent? On the other hand, a line which intersects this graph, say this point and at some other point, is quite easy to find. Yeah. Yeah. So eventually we'll do just this, but now, as I said, I mean, we will introduce derivatives in a couple of lectures. So for now we just don't have derivatives. And I mean, maybe it's a good point. So how many of you have never seen derivatives? How many of you have never seen limits? Okay, so everyone has seen limits and everyone has seen derivatives, right? Okay, so I guess I'll still do this example and well, then I'll just do it a little bit faster when I plan to. So the idea is, well, it is hard to find a tangent line just from the picture. But it is quite simple to find the equation of a line which intersects my graph. I can take any point on the graph and this point and find a line through these 2 points. Very easy. Let's say when x is equal to 1, f of x is equal to 2, and I can draw this line. Well, of course, it is not what I want to find. It's not the tangent line. However, it is some approximation. It gives us some information. You see that it is more steep than the tangent line. So its slope, what is the slope? It's the change in y value here divided by change in x value here. So the change in y value is 2 minus 1, is 2 minus 1. And the x value is 1 minus 0. So is 1. So this line, which has slope 1, well, it is an overshoot on the actual slope of the tangent line. So it is overshoot. The actual tangent line has smaller slope. So it is good, but maybe not good enough. We can estimate the slope from below as well. We can take a line which is less steep than the tangent line. We can take a point on the graph somewhere here, say minus 1, with y value equal to 1/2, and draw this line, which is less steep than the tangent line. So for this one, the slope will be, once again, change in y value, which is 1/2, divided by change in x value, which is 1. So it is 1/2. And we see that that our slope is actually some number between 1/2 and 1. So this is an estimate from below. It's undershoot. Well, and the idea, as we suggested, is, well, let's take this point and make this estimate more and more precise. Let's make this point closer and closer to 0. Let's make it, instead of being 1 here, let's make it, let's say, 1/2. We'll get a line which is less steep than this one, and it is closer to the tangent line. more generally we'll take the following. We'll take this graph. On it we'll choose any point with coordinate x and 2 to the power x. And then we'll draw a line passing through this point, 1, 0, 1, and that point. And for this line, the slope is, once again, the change in y value, 2 to the power x minus 1, divided by change in x value, x minus 0. And the next step would be, well, let's try and make x closer and closer to 0. So let's make a table of the slopes. So we know if we take x to be equal to 1, the slope is 1. If we take x to be equal to minus 1, kind of on the other side, you'll get slope of 1/2. And then we can try x somewhere in between. For example, let's try x equal to 1/2. What is this number? Well, it's 2 to the power 1/2 minus 1 divided by 1/2. So what is it? Well, what is 2 to the power 1/2? Square root of 2, right? Minus 1 divided by 1/2, which means multiplied by 2. Which is approximately square root of 2 is 141, minus 1 is 0.41, so it is 0.82. So at this point we get slope of 0.82. It is, well, smaller than this one as we expected. It is larger than this one. And our actual slope of tangent line is somewhere in between. Well, let's keep moving these points closer and closer. Let's take, say, 1/10. Well, you can just take your calculator and find it. The slope here will be 0.717. If I take minus 1/10 to get an estimate from below, I will get 0.669. So now we know that our slope is some number between 0.669 and 0.717. Okay, that's good. Maybe some guess as to what this number is. 0.7. Okay, so sounds reasonable, but if we try the next step, 100ths, it turns out that this slope is 0.695. And just from this graph, we see that this number is larger than the slope. So 0.7 is not the value of the slope. And if we try minus 100, you'll get 0.690. Our number is still somewhere in between. So somehow we still don't have a good guess as to what this number is. Well, we might not have a guess for what this number is, but we have a pretty good estimate for what it is. It is, well, I would say about 693, plus minus 0.01. So we do have a pretty good idea of what it is, we just don't know how to express it in algebraic formula. And if you try x equal to 1 over 100,000, well, your calculator can compute it. You'll get that 2 to the power x minus 1 over x is actually, okay, it is 0.693147 and some other numbers. And actually, if you take plus or minus sign, your calculator will show the same answer. So we'll guess that this number is correct in 6 digits already. Okay, so we get a very good approximation of this number. We still don't know what it is. Well, it happens. So in a way, this is an answer. So we know that the slope is 0.693147. And that's a very good answer. And we actually, well, we didn't find a single derivative. We didn't remember any formula from high school or from anywhere. We just made a direct estimate. How large is the slope? Well, it turns out that this number is actually one of the familiar ones. It is actually 1 of 2. So if you take your calculator and you compute what is logarithm of 2, natural logarithm of 2, then you get the same answer. So this example is an example of another phenomenon. You can take quite a natural, let's say, problem. What is the slope of a line, of the tangent line to the graph of exponential function with base 2? Just a function which doubles at every step. Kind of natural question. And the answer turns out to be expressed in terms of logarithm with base e. So somehow this e, which we introduced last time as being just basically 2.71 something something, well, it does appear quite naturally in many problems. So somebody wants to ask a question here. Okay, so any questions about this? Another comment. Well, this number is what these numbers in this row converge to as you make the number in the first row smaller and smaller. You just see it from the table. It is a natural thing to try, well, what happens if I take x to be exactly equal to 0? Maybe it will produce me exactly the value here. Well, unfortunately, it doesn't work this way. If you take x equal to 0, 2 to the power x minus 1 divided by x, well, what is it? It is 2 to the power 0, which is 1 minus 1 divided by 0. So it is 0 over 0. Does it look like logarithm of 2? Well, not at all. It is just not defined. So even though the natural thing here would be to say that at the point 0, this value has something to do with the point 0 in this table. However, it's not the value of this function at this point. It's really not. There is no value of this function at point 0. The way we express this idea is limit. We say that limit of 2 to the power x minus 1 divided by x as x tends to 0 is this number, 1 of 2. It's really not that easy. I mean, this limit is actually not that easy to compute if, well, not numerically. Well, you might know how to do it, but still, it is not the easiest possible limit. So here it just demonstrates the concept of what limit is. We say that a function has a limit at some point if whenever the parameter is close to this point, the function is close to the value, like in this table. So first let me write the definition of limit, then say a couple of words about what it means. So limits, we say limit of a function f of x in point A is equal to some number L if f of x becomes, well, gets closer and closer L as x is closer So the notion of limit is exactly what describes this situation. When we have a function we have a function f of x, and for it we want to evaluate what is the limit at point A. So the notion of limit is exactly about such a procedure. You take a point A and you take points nearby, minus some small number, maybe minus 1, A minus 0.1, A minus 0.01. And from the other side, A plus 1, A plus 0.1, A plus 0.001. For each one of these values, my function has some output. Well, it will give me some number here, some number here, some number here. So for each input, my function gives me an output. The concept of limit is what captures this point in between. It's what the values of my function converge to as my parameter converges to the point A. So for this function, 2 to the power x minus 1 divided by x, at point 0, we just actually computed what this limit is using the definition. We took numbers which are close to 0 and we looked at the values of my function. Of course, we are not going to do it every time we see a limit. Sometimes it might be quite obvious what the limit is. For example, limit of x squared plus 1 as x tends to 1. What is it? 2, right. And the reason is, well, according to the definition, what should we check? We should check that when x is close to being 1, the value of this expression is close to 2. Well, of course it is. When x is close to 1, x squared is close to being 1 squared, which is 1, then x squared plus 1 is close to being 2. So no problems in this example. Another example. Limit as x tends to 0 of x over x. What is this one? 1. Right. Okay, so it is actually 1. Let me give you a wrong argument for why it is 1. And then somebody will correct it. So it's wrong. Well, what I'm actually after is, let's say, the value is 0. And it is 0 divided by 0, which is 1. Is this the correct solution?
No.
Okay, why it is not the correct solution? Okay, so yeah, why it is not the correct solution?
X is approaching to 0, so everything that's approaching 0 is still like a number. So
Okay, yes. So one reason, it is wrong for two reasons. One reason is that's not what the question is asking. It's not about the value of this function at the point 0. It's really not about plugging in x equal to 0 to this expression. Limit is about when x is close to 0, but not equal to 0. So this part is already wrong. I shouldn't have started even to plug in x equal to 0. And of course there is a second mistake. 0 divided by 0 is not equal to 1. It is not defined. So this is wrong as well. The right argument would be, as you said, well, when x is any number but 0, in particular if it is close to 0 and very small, x over x is just equal to 1. So of course, if I just do my table like this, and instead of f of x I have x over x, and I compute it at every point, I will get 1, 1, 1, 1, 1. Of course the limit is still 1. Kind of extend this example. What is this limit? X squared over x as x tends to 0. Somebody should say it loud.
0.
0, right. So the reason here is, well, let me write the reason. For every point where x is not equal to 0, this expression is equal to x. And of course I'm interested only when x is small, close to 0, but not exactly 0. So this is the same as limit as x tends to 0 of x. I can't, in general, just cross out one of the x from the numerator, because it might be 0. But because I'm talking about the limit, I can. In this limit, x is close to 0, but not 0. So it is 0. Okay. Maybe last example for today. Limit x squared minus 1 over x minus 1 as x tends to 1. So what about this one? 2, right. And the reason is very similar to the one here. Well, the reasoning goes like this. When x is close to 1, first attempt is to try to see whether I can just argue it as easily as I did here. When x is close to 1, the numerator is close to 1 squared minus 1, 0. The denominator is close to 0. What can I say about the quotient? Well, nothing. If I divide one small number by another small number, I just don't know what the answer is. However, here they are not just arbitrary small numbers. They are dependent on each other. More precisely, the numerator is in fact the product of denominator and x plus 1. So now I see that I have a number times x plus 1 divided by the same number. And this number is not equal to 0, because x minus x is close to being 1, but not exactly 1. So the difference is small, but not 0. So that's the same as limit x plus 1